Now, two teams of researchers are in an international race to find the answer to one of the biggest questions in life. Why does our universe exist?
It's quite big for this time of the morning.
Even bigger than Brexit deals. Yeah.
Scientists in the US are hoping their new particle detector could offer an explanation. But a rival Japanese team is several years ahead with its own version. So who will find the answer first? Here's our science correspondent Pallab Ghosh to explain.
Nestled above the mist of the forests of South Dakota is a lab like no other. Inside, scientists are searching for the answer to one of the biggest questions in science. Why does the universe exist? The answer lies deep underground. They used to dig for gold here, but now, for the scientists here, they're searching for something even more precious.
We're 1,500 meters underground in this cathedral for science. We're poised to begin construction of the detectors that will change our understanding of the universe, answer the question of why we exist.
When the universe was created, scientists believed there were two kinds of particles. There was matter, from which the stars and galaxies and everything around us was created, and then there was antimatter, its exact opposite. Theoretically, the two of them should have combined and cancelled each other out, leaving nothing but a big burst of energy. Yet here we are. Scientists believe that the answer to why matter won that big battle and the universe exists lies in studying a particle called the neutrino and its exact opposite, the antineutrino. Scientists will be firing both particles in beams all the way from Illinois deep underground to detectors in South Dakota to find out what the differences are. If they find a difference, they'll have hit the jackpot and found a key difference between matter and antimatter that will bring them a giant leap closer to explaining why the universe exists the way it does. Half a world away, in this beautiful structure, Japanese scientists are using golden globes to search for the same answers. They're building a lab called Hyper-K, which will be a bigger, better version of this existing detector.
We switch on earlier and have a larger detector, so we should have more sensitivity sooner than June. But when you take the experiments together, we learn a lot more that you wouldn't get with them both individually.
So having two experiments is the best of both worlds. Together, they're greater than the sum of its parts.
Exactly, though I'd like to come first, please, still.
The race is now on, with the first results expected in just a few years. Pallab Ghosh, BBC News.
I told you so, it's dead simple.
So I know it all now.
My head hurts. Let's try to get some more answers. We're joined by the physicist, Dr. Kate Shaw, who's from the University of Sussex.
Help!
Hi, good morning.
Help, yeah, that's exactly. I mean, it's a big question.
Yep.
It's the ultimate question.
It is indeed.
Will we ever really get an answer?
So we are going to very soon get an answer. This is why it's a really exciting time for particle physics. We have these two experiments. The one I'm working on is called June, the Deep Underground Neutrino Experiment. And hopefully it's going to finally explain to us why any of this is here at all.
I mean, you might have to explain a little bit more about. First of all, why do we need to know? Why is it so important to know this?
So, well, at the beginning of the universe, according to our theories, there should have been an equal amount of matter and antimatter created. And of course, now we live in a matter-dominated universe. So we need to understand why there is this asymmetry between matter and antimatter. And we are pretty sure that neutrinos should have the answer.
Neutrinos?
Yes.
Are neutrinos a new kid on the block when it comes to this kind of theorising?
So no, actually, neutrinos we've known about experimentally since the 1950s, but they are as near to nothing as any particle can be. Neutrinos have almost no mass. They have no electric charge, but yet there are billions around us all the time. In fact, trillions are going through our bodies right now. They go straight through us, straight through the Earth, and continue on their galactic adventures across the universe.
Wow.
The structures that are being built, I mean, that one in Japan is extraordinary, that golden kind of dome. Yeah. And the one that's, it's the one that you're working on, June, a little bit further behind then in terms of the sort of construction?
Yeah, so in particle physics, we're always on the scale of decades rather than years. Hyper-K in Japan, that will be coming online, I think, 2027, and the Dune experiment will be in 2029. So
can you just explain what we're looking at?
It's like looking at Doctor Who, isn't it?
Yeah.
It's amazing.
It's beautiful, isn't it? So this is Hyper-K. This is the one in Japan. It's built on very standard technology. So these are all called PMTs. They're little kind of inverse light bulbs. They absorb the light from when the neutrinos interact with the water inside of the detector.
And so they're busily doing that in Japan. Meanwhile, the Dune project and the American team with the UK support is underway as well. There we go. That's it.
Yeah.
I mean, wouldn't it be better if you all just worked together and did? Because I guess you're going to come up with the same answer. You would hope.
Yeah. Well, that's exactly what we're doing, actually. So for any scientific experiment, you need to have two independent experiments to be able to verify any measurement. So we are, Hyper-K and Dune, we're all colleagues. We're all from international collaborations that know each other very well, and we will combine our results. But the two technologies are different, and you need to have that to verify that your measurements are correct.
So what timescale are we looking at? I mean, I was very impressed that when you said, are we going to get an answer? You are absolutely, we're going to get an answer.
So we don't get many here sometimes.
Well, no, quite.
This is why it's a really exciting time. There's some really big questions we have in high energy physics and particle physics and cosmology about the universe. And it does take decades to find answers to some of these questions. So knowing that both these experiments are coming online very soon, throughout the 2030s, we should finally get a result and an answer to why matter is here and why we are here at all.
And how excited does that make you?
Oh, it's really exciting. It's really amazing for our generation and also the next generation of students coming in to really attack some of these big questions in physics.
And then what? Once you've worked out that,
well, the thing with physics is every time you answer a difficult fundamental question, unfortunately, it opens the door to a whole new area of physics and more questions that come up.
Well, it's fascinating. It really, genuinely, it's really genuinely fascinating. And good luck with the build in the States. And we'll keep checking in. What would say? Then the 2030s we're expecting.
Yeah, 2029 we should go online for June.
Brilliant. OK, Dr. Kate Shaw from the University of Sussex. Thank you.
And if you find out why the university exists, do give us the exclusive. We'd love that.
Will do.
It's 6:57.
Time now to